exploration. Why do we have to get into space exploration? Most times, if we follow the history of space exploration, we know that most times it's because of maybe cultural and a bit of political national prestige. If you remember, the Soviet Union and the United States, they were almost competing among themselves to see who was going to be superior in space, and ultimately, you see the first spacecraft was Sputnik, the first dog Laika, the first man, the first woman, all by Russia, the former Soviet Union. And then America felt a little bit humbled, and they had to do something. So political and national prestige also play a very important part. Of course, scientific knowledge, we want to know more about our environment. At the same time, we want to know more about the cosmos. Beyond Earth, what are all those things over there? So space exploration actually extends our knowledge about the cosmos. Then another one is just assurance of human survival in case of any cataclysmic event. We all heard about the disappearance of the dinosaurs 65 million years ago when there was an asteroid impact. So what happens to human race if there is something cataclysmic? So we're also looking at that. And of course, it's part of inspiration for all generations, both young and old. I've been privileged to talk to young people, and we discuss space exploration. You see their eyes light up when we start talking about astronauts and some other features that has to do in space exploration. So all that. Then, of course, we're extending, like I said, our presence in the solar system. So there are some destinations that are actually very, very interesting, and those are under consideration for now. Of course, people are saying that we're going to reach the stars, but of course, the distance between the Earth and the stars, or we can say our solar system, and the nearest star, Alpha Centauri, that is really very, very far, 4.3 light years. But we have areas where we can visit here, which is the bodies in the solar system. For example, we have near-Earth asteroids. And of course, recently, I'm sure you've heard about Hayabusa and some other spacecraft that have visited some of the asteroids. Like recently, we have OSIRIS-REx that actually came back with samples from the asteroid Bennu. We also have the moon. Humans have landed on the moon, and hopefully very soon in the nearest future will be on the moon. And of course, recently we see how the Pragyan, which is like the rover from the India Chandrayaan lander, and at the same time we have U-2 from China on the surface. Then the future, we are thinking about going to Mars, and of course people ask question, why should we go to Mars? Because that's where we have consumables that can actually sustain life. For example, despite the fact that Mars is not that hospitable for humans if you have to go there, at the same time, if you have to go there, you have those consumables that you can use, and at the same time sustain life. And through in-situ resource utilization, you can actually get some materials that you can use to survive. So that is why Mars seems to be the candidate that we are thinking of if we really want to extend our presence and stay in the solar system. Then we have Curiosity, Perseverance, and Zhurong rover. Zhurong is from China. And of course, we're always thinking about colonizing Mars all the time, reforming and all that. It's going to take time. But what is going to happen is that it's going to take a lot of effort from people for you to be able to build up a city on Mars. Most likely, you have to actually make materials from the surface. You have to actually use materials from the surface if you want to build, because if you... Please, can you mute your phone? Your mic.
So guys, whatever happened, I'm sure it will join back. Maybe something happened with the connection.
Okay. I want to go check.
Hello.
Okay, he's back. He's back. He's back.
He's back. I think
Hello,
it's,
sir.
I
Thank you
think
for joining back.
yes, we lost.
Happened.
Yeah, something happened. It just went off. I'm trying to connect again now.
Okay, all right. Thank you.
All right. So we share the screen again. I think we are here. I think it's maybe the network or something. Let me share the screen again. So so we have the dream of going to Mars and to colonize the place. And according to Elon Musk, we are supposed to have big cities on Mars and all that. And all this require lots of infrastructure to be able to do that. A lot of institute resource utilization and other things are involved for we to be able to achieve all this. Space exploration of planets, other regions of our solar system have become active, exciting field of research. And of course, we have so many outside the solar system. And of course, it is increasing. I think the internet is a little bit unstable. Let me, all right. So, sorry about that. I'm trying to change the network to see if I can actually stop all that. All right. So back to that. We have to actually try as much as possible if we have to become multi-planetary species. And I think one of the ways we can actually do that is by using robots in space. And of course, robots can either be precursors, pathfinders. Pathfinders are people that actually, or machines that go ahead to seek out and to find out the nature of the environment then before coming for humans to even to go there. You remember when the Americans went to the moon, we have so many precursor missions like the Ranger, Surveyor missions, before we now had the Apollo missions landing on the surface. So we have robots too that can also do that. Then the definition of a robot. And we know that a robot is a machine or device that operates automatically or by remote control and is capable of operating maybe complex tasks on command or autonomously. The important thing here is on command autonomously. So that means it's possible for you to, in real time, command your robot, but at the same time, it's also possible for you to maybe leave it to perform autonomously. Most of us are probably aware of different kinds of robots. For example, those ones on wheels. We are so used to robots on wheels all the time, but at the same time, we have robots that are either bipeds and quadrupeds. It's not really a big thing. A biped is 2 legs. Then quadrupeds, for example, goats have 4 legs, so they are quadrupeds. And human beings are basically bipeds because we use 2 legs to walk. So we have robots now. For example, here we have samples from the Boston Dynamics, where you have biped robots and quadruped robots too being tested. Some of you are still unmuted. Please, can you mute yourself? Then 4Ds of robots. There are 4Ds of robots. That's just the mantra that the robots are supposed to have. For example, they operate in dangerous, dull, and repetitive area. difficult, dirty, and harmful. In our own case now, we are looking at a space environment that is extremely very, very harsh and dangerous if we don't protect ourselves. So robots can actually play a very powerful role in that area. So space robots are actually designed for the space environment. And of course, you know, space actually is above us. Like once you enter the command line, like 100 kilometers, then above that, everything changes. Even if you're inside the space, inside the aircraft, you see that it's kind of pressurized for you to be able to survive inside, for you to be able to maintain normal pressure. But in space, it's absolute, almost vacuum. So what you're trying to do is, if you have to survive there, is to be able to carry something that will help you to survive. In some cases, people use spacesuit. But for a robot, it's possible for you to actually build a robot and put it in space, and at the same time, it should be able to survive there. And they're very, very expensive to design and produce, but if you lose a robot, it's more preferable than losing an astronaut. Then there are different types of robots, different types of space robots. For example, we have, I think someone did not unmute. Someone did not, please. Okay. All right. Space robots play various roles. And of course, just like you have different machines on Earth doing different things, you have different kind of robots depending on mission profile. The precursor robots, like I mentioned the other time, they go before humans. Before humans go to a particular place in space, you have precursor robots going there, maybe to test, to see what is happening. For example, if you remember the surveyor during the lunar landing missions, actually landed on the moon to test the stability of the lunar soil in case the lunar rover lands on the lunar module lands on the surface. So that be able to determine, okay, is it stable for humans to actually land on that surface? So we have exploration robots that actually, what they do is actually to go there and explore, and we have like opportunity zero. Then we have the assistance robots that actually help the astronauts to actually provide mobility for the crew. Then the caretaker robots who work on the crew vehicles to assist, clean, and in the future, there are going to be so many of them. They are going to help fix the vehicles, and they're going to make sure that everything is in shape. For example, some of them are like the Robonaut, and at the same time, the Astrobee. Then we have different constraints if you have to fly a robot to space. One is the mission objective. What do you want the robot to do once it gets to space? That then at the same time, the profile, how is it going to fly? Where is it going to fly from? Then where is the destination? All these things will determine the constraints. Those are like the constraints that are going to determine whether your robots will be able to perform or not. Then at the same time, the cost. Do you have the money to be able to design the robot that you want to fly? If there is no money, it becomes extremely very, very difficult. For example, Curiosity and Perseverance are almost about, I think, $2 billion. That's very expensive. But there are some robots that are more cheaper. Like if you look at the Indians, they are able to produce cheaper robots because of the way they are designing it, and at the same time, because of the available money that they had. And of course, you see this also have effect on the size of the spacecraft and the robot they're able to produce. And at the same time, maybe the lifespan of the mission. The bigger it is, the more likely that it's able to stay for a longer time. Then the vibration during the launch. If you have a robot that has to fly, you have to make sure that it's able to survive the launch of the rockets. For example, there is so much noise and at the same time vibration. If it's not well designed, it's not going to end up performing the mission that you set it out to do. Then the environment, you should be able to survive in space environment, like we discussed earlier, and at the same time, the duration of the mission. If it's a 1-year mission, you have to make sure that you design it to be able to last for 1 year and more. If it's just for 1 week, you design it that way. Then power is also very, very important. In fact, if you watch this movie, Apollo 13, I think I would advise, if you haven't watched it, watch Apollo 13, you see John Aaron saying power is everything. if you go to space, what you need for anything you are doing is power. If you need to rearrange your spacecraft, if you need to send data, if you need to download data, if you need to move mobility, you need power for everything. So power is also very, very important, as we all know. And if you are designing robots for space, they are quite different. They are quite different from those that you have on Earth. Like I mentioned, some of the constraints that we discussed before actually affect how they are developed. And of course, you have to remember, like I mentioned, the environment, which like the zero-G environment, in weightlessness, they should be able to perform in that environment. So in that case now, in a weightless environment, you must be able to factor in that zero-G in your design so that you'll be able to perform. For example, you see made in space 3D. In fact, I think I was fortunate to be with those guys when I was at NASA Ames. And you see the constraint that they had when they were designing was trying to make sure that they're able to 3D print in a weightless environment. So also when you're designing, you have to make sure that that is taken into consideration. And of course, the vacuum and the thermal conditions of space, you have to also consider that. Remember here, you can cool down your system with convection of air, but over there, you don't really have this convection. So that means we must do active cooling or passive cooling, depending on what is needed. Then high energetic particles from the sun and the galactic cosmic rays can actually cause electrical, electronic, and component failure. So you have to also factor this. Are you going to do radiation hardening for your system so that they'll be able to perform optimally? So what are some of the considerations for optimum performance of robots in space? Mobility. You must be able to move very quickly and precisely where you want it to go. Because anytime you waste, you're actually wasting power. So that means beforehand, you must be able to define where you want your robot to be. And at the same time, you make sure that it goes there. All right? Then manipulation. You should be able to move the arm if there is an arm, all right? And at the same time, the end effectors, those are the grippers. They should be able to make contact with the sample the way you want them, the adequate pressure. Is this something you don't want to crush? So that means it has to be very, very subtle. Then it has to be quickly, accurately, and safely. Then the extreme environment, it should be able to perform in extreme environment. Remember, it could be very, very cold. And of course, the temperature could fluctuate. For example, on the moon, it could be as high as more than 150 degrees Celsius at times. And in the night is minus just sub-zero. So that means you have to be able to design if you want your spacecraft or your rover to survive for that duration. Then ionization, as I've mentioned with the high energetic particles, you need to be able to kind of do a bit of radiation hardening so that your electronics are not fried on the surface of wherever you want your spacecraft to be, or maybe wherever you want it to orbit. Then at the same time, you have to consider time lag when you are operating your rover, because if you are transmitting for someone on Earth, I'm sure you experience this. If you have an uncle somewhere in US and is calling you, there is a little bit of lag because of the light time delay and some of the equipment, maybe the fiber optic cable below the Atlantic takes time to be able to move it there. So all those things are really very, very important for you to actually consider when you are designing. So time delay is also very, very important. What this means is that you need autonomy for that spacecraft. So that is what now we circle back to initially. Remember we said autonomously or on command. So you should be able to do that. So why do we need autonomy for a space robot? Okay, like I mentioned, the time delay transmission. It takes longer time. The farther you go from Earth to wherever your destination is. For example, from Earth to the moon is like 1.25 seconds. So that means once you are transmitting to your rover on the moon, it takes like 1.25 seconds for the rover to get your transmission. And of course, routing the response back again, we probably, if it's instant, it's going to be exactly that time again. So it's taking almost like 2.5 seconds for you to actually have maybe around about kind of discussion or communication. And in case of an emergency, it's also very, very important for you to have that autonomy, like I said, so that the robot will be able to carry out activities without any hindrance, so that you don't damage the robot. For example, if we look at Mars, for example, the average distance between Earth and Mars is about 225 million kilometers. And of course, one-way communication is about, if you do the math, is about 770 seconds. Yeah, that's the speed of light. That's 3.8 meters per second. It takes about 370 seconds for you to get your transmission, your data, down to a rover on the surface of Mars. That's about 12.5 minutes. Now try to imagine if there's maybe something, an emergency. Is it going to now take you that long for you to be able to respond? So that's going to be something that you have to consider. So as much as possible, you make sure that you factor in a bit of autonomy inside your spacecraft, your rover. It's very, very important. Then at the same time, you look at the size and landing complexity of various landers. And of course, here we have different landers and rovers on Mars. For example, left here we have the Viking, then the Phoenix lander, and of course the Spirit and Opportunity. And lastly, we have an artist's impression of the Sky Crane landing of both Curiosity and Perseverance rover. And of course, you can see the profile, the entry, descent, and landing, which actually is a very, very critical part of landing on the surface of any other planet. You have to take care of the environment. You have to make sure that your spacecraft is able to land safely first, before you are even able to deploy your rover. And you see, for very light, in quote, rovers like Opportunity and Spirit, about 185 kilograms, you can use the airbags to land them on the surface. But if you have something almost 1 ton, just like the Curiosity and the Perseverance, you need a new mechanism and a new device to be able to land them safely on the surface. And in this case, now we have Sky Crane maneuver. You should watch 7 Minutes of Terror for you to be able to understand and see how they were able to carry all this out. And one thing that is really very important is what is called the terrain relative navigation that was used to land Perseverance on Mars. And this is actually introduction of artificial intelligence in London. In the olden days, you just look at the velocity vector and of course some of your sensors trying to take, okay, what is the effect of maybe draft of the wind on the spacecraft? Based on that, you're able to calculate and infer what the velocity is. But in this case, what happens is that, okay, we have taken an image of a particular place on Mars before. What we're going to do is to load it into the memory of the spacecraft landing. Once it's able to match that place, then it picks exactly where it's going to land. And of course, this technology improves the probability of safe landing of the desert region. And what Perseverance actually did was almost like a pinpoint landing because of artificial intelligence. And now we have so many rovers on Mars, from Pathfinder now to the Chinese rover Zhurong that is on Mars now. And of course, we don't have to forget Ingenuity Mars helicopter that is on Mars. Let me just talk a little bit about my experience in robotics. I was fortunate to go to NASA Ames for a fellowship, and there I was involved with a team that built what is called the Lunar Micro rover. And of course, as you can see, the name is Micro, so it's a very, very small rover. And the project started in 2006. And when I was there, it has actually gone through 6 iterations, 6 different designs. What we don't really understand or know is that at times when you have a mission that actually flies, some of them would have taken almost like 10 years for them to be able to get to fruition, because there's so many things you have to keep up refining. And at times, positively, you have things like technology that you want to develop. For example, the Parker Space Probe, the heat shield on that probe was not really, they were not able to actually fine tune it until recently before it was now launched. So at times you have to wait for the right technology. And there are so many things that we've been doing with the Lunar Micro Rover. It is a very small rover, and you can see the iterations there. And of course, the goals, maybe to transverse lunar surface for about 100 meters. So that means the objective, once it's able to move up to 100 meters, that's okay. Then the camera subsystem should be able to capture low resolution video images, low resolution. And this is at about 5 frames per second. Your normal video that you watch is about 25 frames per second, and you have the American version about 30 frames per second. So imagine that means your 5 frames per second will be extremely very jerky, but at least it gives you a sense of what it looks like on the surface of the moon. And of course, acquire high resolution images by capturing panoramic image photos. So that means it will just rotate and take panoramic images. All right, then it should be able to survive lunar environment for 2 hours. Remember, it is very, very small. That is why if it's able to survive the environment for 2 hours, that means the mission is met. And of course, it is less than 10 kilograms. Remember I said Perseverance rover is more than 100 kilograms. That's more than 1 ton. More than 1,000 kilograms. That's more than 1 ton. Now, for us to have 10 kilograms, that's 1 over 100 of the size of Perseverance rover. All right, then we then plan to achieve this with $500,000. And of course, it's still being reiterated. And I think based on what I heard, it was not able to fly because of funding issues. And of course, some of the things that were used for the mobility system, aluminum was used because we wanted it to be as light as possible. Then titanium outer hub, then different kind of motors, I think brushless also. Then the structural integrity, everything was just carved out of 2 materials so that we don't have different kind of sections. And of course, it is going to be conduction cooled, because if you look at the wheels, it's such that it could lose heat, maybe through radiation, and at the same time through contact with the surface and all that. And of course, to be able to do all this, we have to find a way to compress the images. Like when it comes to capturing the images, you have to capture. And remember, this is like 2011, 2012. We don't have some of the very good cameras that we have now around. And of course, the goal was just to compress as much as possible, because you want your data rate to be as low as possible when you are transmitting, and everything has to be compressed. And of course, this is just like a picture of myself walking and driving. The rover by the left is somewhere in, I think, Utah desert, and we had to control it from NASA Ames in California. You can see the picture of myself. So at the bottom right, we have team members of the Lunar Micro Rover. That's actually where we were controlling from, as you can see. If you look at the machine I was using to control, and the one on the table at the bottom right. And of course, that's the 3D at the left bottom of the rover. Then pertinent questions about exploration of this space. This provides opportunity for the young ones, because we have so many questions that we ask ourselves. How do we transport astronauts and consumables? Of course, we are looking at optimum ways of doing that. How do we protect the crew and equipment, even robots, when we are transporting them in space? Then in the future, when you have astronauts and at the same time robots going to space, how do you sustainably provide food for the crew? is also very important. And how do we reduce the workload on astronauts? And how do we complement their work with robotic operations? Then what contribution can we make as young people? There is something that I believe that is an advantage. We have what is called the youth power. If you look at this graph that I made in one of the book chapters that I made, that I wrote, you can see the population of people in Africa that are under the age of 25. That's 60% of the population of Africa. That means we have very vibrant population. Despite the fact that we have about 1.4 billion people in Africa as at 2021, 60% of these people are under 25. And this is an advantage for us because younger people are usually more technology savvy and they are full of energy and have skills. And this can be unleashed in the different countries of Africa for us to make progress. So for successful robotic teams, there are so many takeaways which I feel that you can have. One, teamwork is very, very important. You need to make sure you understand that you're part of a team and you are doing one thing just to make sure that the mission is successful. Either you are in the design, the hardware, the power, the electronics, the software. What is very, very important is that you are heading towards a common goal. And in all space robotics projects, this is really very, very important. You can see how complex perseverance is. If you go on YouTube and check out different wiring systems, different mechanical systems, different electronic systems, software, but everybody knows what he or she has to do. And of course, at the end, the mission was very successful. So if you want a very successful mission, maybe in your robotic teams, so as much as possible, you must know that you're working towards a common goal. So thank you very much. So I don't know if you have questions.
Thank you so much, Dr. Samuel, Anih. We are so grateful for this session. It was very, very insightful, so informative, and it just, I don't know, it's just uplifted me and the tiny ideas I had about robotics and all of that. You're super welcome to this great event. We're so grateful to have you here. Is there anyone in the audience that has a question or comment about this session? Please raise your hand or go ahead and speak. So I'm going to be reading the chat and see if we have questions. We're waiting before we move ahead.
All right.
Anyone? Okay, so we have Nelly. Nelly says, I have truly learned a lot. Thank you so much, sir. Yeah, right. Great. Okay, so while we're waiting for people to indicate that they have questions, sir, can you please throw a little bit more light on this conversation? Like, how do you think Nigeria can move forward, like from your own perspective, and what do you think are current challenges locally and internationally as well?
Okay, in terms of space robotics, right?
Yes, sir. Yes, sir.
All right. All right. The world is already global. I think in our days when we were younger, it's really very difficult for you to really get knowledge from other parts of the world. And now, like you are having a space generation Congress meeting now with different people from different parts of the world. I believe Abraham is in the US and is participating. So that limitation is gone. What happens now is the zeal that you have as a person for you to be able to participate. In fact, there's no limitation. on what can really happen. You see young people, even Nigerians that are abroad, they're really making waves in robotics. It's not that it's just because of what is, they actually got interested in space, and at the same time now thought, okay, why don't I just move into robotics? And gradually, if you're in the STEM field, you can actually move into robotics. And let me tell you, robotics, like I said, is not just, there's nothing like a robotics engineer. If you're a roboticist, it's either you're a mechanical engineer, electrical engineer, electronics engineer, you're a designer. There are so many things that you can actually be part of. So it's not limiting you to one area. And with that, you can actually play a role, even if you're an artist. Some of the simulations and some of the artist impression, for example, if you go on YouTube and you see 7 Minutes of Terror, I was able to converse with one of the guys that used to do some of those things. He is an artist, but he's able to move the things so that you're able to see. Nobody has a camera and is pointing it maybe on the spacecraft landing on Mars. But what happens is that he's able to do an impression of it. He is not a scientist. He is an artist. So he's playing a role. And some of them work with NASA, some of them work with the European Space Agency. So that means, what is the niche? What is the area that you are really very interested in? All right? And you have passion about. Once you are able to identify those areas, then you can just go there, then develop it, okay? And then move very, very fast and be able to play a role there. Then when you have people that are actually versed in this field, you can interact with them. You can talk to them. You have Dr. Uma in our university, you can talk to me. So the limitation is no longer there. So if you're passionate about it, most people now just go to YouTube. I think YouTube is the second largest search engine now. Go there, search for whatever you need, is there. So what is really very important for you is your passion for what you want to do. As much as possible, if you have that passion, you'll be able to get there. I think that answers the question.
Right, absolutely. So the first step for someone to do, or from what I got from what you just said, is to find a specific niche that someone is interested in, and then you just follow it and then look for someone that you think you can have as a mentor, and then just follow the person, and and people can also reach out to you. Okay, so we have a question in the chat. The doctor mentioned about building space robots and having an opportunity to work at the NASA team. How can we have spaces where young people can build these robots? From my experience, I think open space and maker space where people can build stuff aren't that common around here. Okay, so basically, I think this person is asking about, okay, so this is from Dara Obademi. Dara Obademi, thank you so much for your question. So I think what he's trying to ask about is opportunities, and probably if there are organizations people can join, or clubs thereabout.
Yeah.
Dara, I hope I got your question right.
Yes, that's sort of my question is around finding
you can
maker
access,
spaces. Yes, because when it comes to building hardware, because of one, the cost, the challenge of infrastructural support, it may be quite tricky if you don't get that infrastructural support and base. So that makes it much more different from software where you just need a computer and internet and electricity to just write your code on the system. So that's my question. Like working in the NASA space gave him a lot of opportunity to leverage on the system NASA has. They have the materials to work with, the other people to share ideas with, and things like that, sir.
Yeah, I understand you, but you are talking about high level now. I think the question should be, what should be the step you have to take before you get to that level? You are looking at people building a flight-ready robot, but we are talking about starting. As an individual, most times now, robotic missions are actually funded by countries. So that means if you have countries that are into space flight, they can fund all those things. But for you to start, which I believe should actually be the question, you must start small. Are you in a robotics team? What do you do there? That is what is going to add up to your profile. Even before I went to NASA, they check your CV to see what you are doing, all right, before you get there. So for you to even get to like the makerspace and all different places you mentioned, you can't just hope from your university and just fly and just go there. You need to be able to present something. Okay, you have your reels, your maybe something to show what you've done before. I was in so team. This is what we built. We use Arduino, Raspberry, things that are very cheap, that some of you can actually get money and build. You use locally sourced material, yes. Then, but of course, your theme, for example, can be a rover, maybe sourcing materials on Mars. Of course, you know you are doing it on Earth here, but at least that theme is what people are going to look like. And it will now provide you opportunity because they've seen, okay, where your interests lie. But if you feel that, okay, it's going to be a straight way directly to working with NASA and building robots, that's not the way it goes. Most of if you go and check it, most people will tell you that someone checked what they've done before. And based on that, even if I'm to assess someone, what have you done before? Because that is the only thing that can prove what you are going to do. But if you just come to me and tell me, whoa, I want to work in your company, I want to work, I will ask, okay, what have you done before? That is it. So as much as you don't have enough infrastructure, you can start small to build something that is very, very close to what you think that the other ones can be. For example, a rover that does something on Mars, a rover that does something on the moon, then you are factoring in some of those constraints that we measured. And how can it take pictures? Things that you can. Based on that, then you have them on your CV. Then you can now apply whenever the time is right. Of course, you have to study too, all right? So you have very good grounding in what you have to do. So my advice is start small, have something to show for maybe your robotics journey. Then I believe sky will be your limit. I think that answers the question.
Yes, thank you very much. Yes, it does.
Yeah.
Thanks so much. We'll take the next question now. Does anyone have a question or a comment? The floor is open. While we're waiting for the next question, I would like to ask, do you have any specific organization or organizations that you would advise that young ones looking to join space robotics, engage or get themselves involved in?
Well, one of the groups is the group that you are in. I think that even makes some sense. And of course, in various centers, like at our center in ARCSSTEE, we have what is called the space clubs. And these space clubs, we encourage them also to do robotics work. And like I said, it's just very, very small because of, like you mentioned, the infrastructure and all that. And at the same time, you need to go online and find there are so many people that are working, all right, on different kind of projects, robotic projects. If you go to Reddit, there are so many people working on different kind of projects. And of course, I know if you go to GitHub, you probably see so many projects that people have done. So you can do a search and you get so many of those people that have even left open source, some of their materials there that you can actually use. Then I think you basically just Google it. You are going to see so many of them. All right. And there are schools that are into that. There are robotics clubs that are into that you can actually join. I believe those are some of the things you can just do if you are really very, very interested. I believe with the internet now, you can actually get, most especially in schools, like I believe now university has a robotics team. With that means they are working on something. And even NASA, European Space Agency, and some of them, they also have maybe calls for people to join. But there are so many restrictions because of maybe nationality. So that's going to actually restrict where you're going to work. Like when I was at NASA, there were so many restrictions I had because I was not an American. Even Canadians too had restrictions. So it's not just, we're not discriminating. It was just, I think that is what the law is. So that means there are open source teams that you can actually get to. Go online, search for them, then you filter out, then before you know it, you should be able to get. And like I said, in our center at ARCSSTEE, we have space clubs, and of course, space clubs, individuals, some of them have robotics clubs. We also once in a while do robotics work. And at times we partner with the university to do some robotics work. Yeah. So that just, I hope that kind of clarifies that area.
Yes, sir. Yes, sir. That was very insightful and informative. So this next question is going to be a little personal, if you don't mind. Looking back on your journey in the space industry, the ups, the downs, you know, everything you had to go through, what you've enjoyed and all of that. What three key advice or what three major advice would you give anyone, just anyone? You could be a lawyer, you could be an engineer, you could be an artist just coming into the space industry and trying to work their way up, you know, and just find your way. Yeah.
Okay, I think, like I said, you have to be passionate about what you want to do. Then you have to be tenacious about it. Don't let anybody tell you no. Okay, so it's very, very important. You have your life to live, and you know what you want to achieve. And even when I had the opportunity to go, the opportunities were not just all over the whole place. I had to look for it, and I have to make sure that I got in. We have so many people, even very, very rich countries trying to get in, but they didn't. And but when they saw my passion, and during some of the interviews, they saw that I was really very, very interested in what I'm doing. Then gradually, that really helped. And of course, I have a background in design initially before I went to International Space University. And that also opened my eyes a little bit about space, to know more. I've been really passionate about space before, even in my secondary school, university days. I had a space club that I even registered with the university. So you can see that the passion has been there. And of course, that passion, like they used to say, it is your luck, but luck is not something that just comes, it's what you make. So if you are really passionate about what you are doing, you will see obstacles everywhere. There's nothing that comes very, very easy, but you'll be able to surmount it. That passion is what is going to help you to be able to surmount those obstacles. All right. And you being able, the ability of you to get there now is the result of you being able to surmount those obstacles. So as much as possible, if you are really interested, then you have to be passionate about it. Now you have more competition because the world is now global. You remember in the olden days, people are known in their locality for being maybe local champions. But now it's Nigeria, before you know West Africa, and you can actually see everybody coming together. So it's possible for you to compete from someone from Azerbaijan. You'll be wondering, wow, how did you know? Yes, you saw the opportunity and decided to apply. And there's this very story about a man from Egypt. I think he was a geologist during the Apollo missions. How many letters did he write when he was applying? He wrote 100 letters. The wife was one typing them out. Then the 100th letter, which he wrote to NASA, was the one that was really answered. Then ended up being the geologist for the Apollo mission. So what happened is like training the astronauts and all that. So most times we tend to give up easily. All right. If you need to travel, if you need to get a particular job, people will tell you, people that really get some things you see in life, they applied more than you did. Some people probably applied 20, 30 times. All right. Meanwhile, some people will apply once and expect the same result. But someone that applied 30 times, 40 times have more chances of getting what he or she wants. So you have to really be tenacious, okay? You have to be passionate. You have to be tenacious. Then don't let anyone tell you something is impossible. You can always achieve it. I think that answers the question.
Absolutely. And I absolutely aligned with that because I mean, oh, so what I got from this is be passionate, be tenacious, and don't take no for an answer. That's super hot. Thank you so much, sir.
Yeah.
I would like to ask that, you know, anyone else that has a comment as we're about to wrap it up, go ahead. And by the way, thanks guys for showing up. Like this is super amazing. Like I absolutely appreciate it. In the event that we do not have any more questions, sir, I would like to say that we, on behalf of SGAC, the event managers and the organizers of this session, really do appreciate your knowledge. I've had a lot to learn from today and it's been an eye-opener. I would definitely have a whole lot of research to do as well. So thank you so much for having us and we'll see you. We'll see you at the event.
Thank you so much. And I wish you all the best.
Absolutely.
Okay.
So,
all right, bye.
This session is going to end in 5, 4, 3, 2, 1. Bye, everyone.
Bye. Thank you very much for a very lovely session. Thank you.